Reductions in PM over decade has improved health, ozone pollution remains little changed. Fewer deaths and serious illnesses have occurred in the U.S. over the past decade as a result of cleaner air, according to a new report focusing on the two most potent air pollutants, fine particle PM 2.5 and ground-level ozone O3. However, these improvements are almost entirely due to reductions in PM 2.5 pollution. The report, presented at 2019 Austrian shillings and published online in the Annals of the American Thoracic Society, is the latest in the annual Health of the Air series produced by the American Thoracic Society and the Marin Institute at NYU. The series estimates health impacts from air pollution for every U.S. city. In Trends in Excess Morbidity and Mortality Associated with Air Pollution Above ATS Recommended Standards, 2008 to 2017, researchers report that mortality impacts of air pollution above these ATS recommended levels fell by nearly half in the last decade as most U.S. counties have seen significant improvements in PM 2.5, while health impacts from O3 pollution has remained stubbornly high. The report's findings are based on the ATS's recommendations for PM 2.5, 11 micrograms per cubic meter for annual concentrations and 25 micrograms per cubic meter for short-term concentrations, and O3, 60 parts per billion, which are more protective than those adopted by the U.S. Environmental Protection Agency. Using air quality data from more than 500 counties with PM 2.5 data and more than 700 counties with O3 data, the researchers estimated the annual health impacts from air pollution from 2008 to 17. In 2017, the most recent year that pollution data is available, the number of excess deaths from air pollution were 7,140 excess deaths from both pollutants combined, down from 12,600 excess deaths in 2010, 3,260 excess deaths from PM 2.5, down from 8,330 excess deaths in 2010, 3,880 excess deaths from O3, down from 4,270 excess deaths in 2010. Based on the levels of the two pollutants, the researchers also quantified serious illnesses, morbidities, and missed school and work days, impacted days. In 2017, the most recent year that pollution data is available, PM 2.5 pollution above recommended levels was estimated to cause an additional 5,600 morbidities and 2,804,000 impacted days. That same year, O3 pollution above recommended levels was estimated to cause 10,080 morbidities and 11,600,000 impacted days. Future health of the air. The latest report found that in addition to the lack of consistent improvement in the health impacts associated with O3, the rate of improvement for PM 2.5 pollution has also started to level off. Without further efforts at the federal and local levels to reduce the two air pollutants, it is likely that the health impacts from air pollution could increase over time as populations grow, according to the authors. The report also highlighted other challenges to reducing deaths and illness due to air pollution. The proposed rollback of several Clean Air Act regulations and the proposed rollback of the greenhouse gas standard for automobiles will make it hard for communities to maintain their air quality, and even harder for cities with poor air quality to clean up, said report co-author Gary Ewert, MHS, Chief of ATS Advocacy and Government Relations. The authors also noted that the effects of wildfires contributing to pollution levels above EPA regulatory levels were excluded from the study, but their increasing frequency and severity may limit the improvements in health that cities and counties can achieve by reducing other air pollution sources. Reducing ozone. Ground-level ozone occurs when sunlight causes a chemical reaction among so-called precursor pollutants, primarily nitric oxides and volatile organic compounds, and forms ozone molecules. Recently, the U.S. Environment Protection Agency designated many locations in the country as being in non-attainment of the National Ambient Air Quality Standard for ozone. States that do not show improvement in the next 3 years will be required to develop a plan for achieving attainment. The large number of adverse health impacts attributable to ozone should motivate cities and states to start now to reduce their local emissions of precursors pollutants, said lead author Kevin Cromar, Ph.D., Director of the Air Quality Program at the Marin Institute and Associate Professor of Population Health and Environmental Medicine at the NYU School of Medicine. Coordinated actions at the regional level, as well as strong actions at the federal level, will also be needed in order to make consistent gains in reducing ozone in many parts of the country. Online tool for cities. The latest report is also available online at http://www.healthofthere.org. There, readers can find lists for the top cities for excess health impacts attributable to the two pollutants, individually and combined, as well as lists of cities that have shown the most improvement over the past decade. In addition, the site includes a map showing the distribution of health impacts across the county. Both the report and the online tool identify the top 10 cities for adverse health impacts from PM 2.5 and 03. Rank city annual excess mortality. PM 2.5 and 03 ranking in 2010. 1 Los Angeles Long Beach Glendale, CA 1322 1. 2 Riverside San Bernardino Ontario, CA 942. 3 Bakersfield, California 293 6. 4 Pittsburgh, PA 232 3. 5 Fresno, California 225 11. 6 New York Jersey City White Plains, NYNJ 188 5. 7 Phoenix Mesa Scottsdale, AS 152 19. 8 Visalia Porterville, CA 131 23. 9 Cleveland Elyria, O 116 8. 10 Chicago Naperville Arlington Heights Illinois 122 4. Rankings based on a weighting of the combined health impacts of air pollution, including mortality, lung cancer, morbidity and impacted days. More information on the annual health impacts from 2010 to 17 for every city and county with an air pollution monitor is also available in the supplementary materials that accompany the published report. Chloroform emissions could delay ozone recovery by up to 8 years. A warming Arctic produces weather extremes in our latitudes. Atmospheric researchers at the Alfred Wegener Institute, Helmholtz Center for Polar and Marine Research (AWI), have now developed a climate model that can accurately depict the frequently observed winding course of the jet stream, a major air current over the northern hemisphere. The breakthrough came when the scientists combined their global climate model with a new machine learning algorithm on ozone chemistry. Using their new combo model, they can now show that the jet stream's wave-like course in winter and subsequent extreme weather conditions, cold air outbreaks in Central Europe and North America, are the direct result of climate change. Their findings were released in the Nature Online portal Scientific Reports on the 28th of May 2019. For years, climate researchers around the globe have been investigating the question as to whether the jet stream's winding course over the northern hemisphere, observed with increasing frequency in recent years, is a product of climate change, or a random phenomenon that can be traced back to natural variations in the climate system. The term jet stream refers to a powerful band of westerly winds over the middle latitudes, which push major weather systems from west to east. These winds whip around the planet at an altitude of roughly 10 kilometers, are driven by temperature differences between the tropics and the Arctic, and in the past, often reached top speeds of up to 500 kilometers per hour. But these days, as observations confirm, the winds are increasingly faltering. They less often blow along a straight course parallel to the equator, instead, they sweep across the northern hemisphere in massive waves. In turn, during the winter these waves produce unusual intrusions of cold air from the Arctic into the middle latitudes, like the extreme cold that struck the Midwest of the USA in late January 2019. In the summer, a weakened jet stream leads to prolonged heat waves and dry conditions, like those experienced in Europe in e.g. 2003, 2006, 2015 and 2018. Machine learning allows climate model to grasp the role of ozone. These fundamental connections have been known for some time. Nevertheless, researchers hadn't succeeded in realistically portraying the jet stream's wavering course in climate models or demonstrating a connection between the faltering winds and global climate change. Atmospheric researchers at the AWI in Potsdam have now passed that hurdle by supplementing their global climate model with an innovative component for ozone chemistry. We've developed a machine learning algorithm that allows us to represent the ozone layer as an interactive element in the model, and in so doing, to reflect the interactions from the stratosphere and ozone layer, says first author and AWI atmospheric researcher Eric Romanowski. With the new model system, we can now realistically reproduce the observed changes in the jet stream. According to the team's findings, sea ice retreat and the accompanying increased activity of atmospheric waves are creating a significant, ozone-amplified warming of the polar stratosphere. Since the low polar temperatures form the jet stream's motor, the rising temperatures in the stratosphere are causing it to falter. In turn, this weakening of the jet stream is now spreading downward from the stratosphere, producing weather extremes. The weakened jet stream is due to climate change. In addition, with the new model, the researchers can also more closely analyze the causes of the meandering jet stream. Our study shows that the changes in the jet stream are at least partly due to the loss of Arctic sea ice. If the ice cover continues to dwindle, we believe that both the frequency and intensity of the extreme weather events previously observed in the middle latitudes will increase, says Professor Marcus Rex, head of atmospheric research at the AWI. In addition, our findings confirm that the more frequently occurring cold phases in winter in the USA, Europe and Asia are by no means a contradiction to global warming, rather, they are a part of anthropogenic climate change. The team's efforts also represent a significant technological advance. After the successful use of machine learning in this study, we are now for the first time employing artificial intelligence in climate modeling, helping us arrive at more realistic climate model systems. This holds tremendous potential for future climate models, which we believe will deliver more reliable climate projections and therefore a more robust basis for political decision-making, says Marcus Rex. During the Arctic expedition Mosaic, which will begin in September and during which the German research icebreaker Polarstern will drift through the central Arctic along with the sea ice for an entire year, the researchers plan to gather the latest ice and atmospheric data. This will help them apply the new climate model to the future, so as to simulate the future development of the Arctic climate and sea ice. As Marcus Rex explains, our goal is to understand in detail how the Arctic sea ice retreat will progress, because only then will we be able to gauge how and on what scale the changes in the Arctic will lead to weather extremes in the middle latitudes. Antarctica losing 6 times more ice mass annually now than 40 years ago. Antarctica experienced a 6-fold increase in yearly ice mass loss between 1979 and 2017, according to a study published today in Proceedings of the National Academy of Sciences. Glaciologists from the University of California, Irvine, NASA's Jet Propulsion Laboratory and the Netherlands Utrecht University additionally found that the accelerated melting caused global sea levels to rise more than half an inch during that time. That's just the tip of the iceberg, so to speak, said lead author Eric Rignot, Donald Bren Professor and Chair of Earth System Science at UCI. As the Antarctic ice sheet continues to melt away, we expect multi-meter sea level rise from Antarctica in the coming centuries. For this study, Rignot and his collaborators conducted what he called the longest ever assessment of remaining Antarctic ice mass. Spanning 4 decades, the project was also geographically comprehensive. The research team examined 18 regions encompassing 176 basins, as well as surrounding islands. Techniques used to estimate ice sheet balance included a comparison of snowfall accumulation in interior basins with ice discharge by glaciers at their grounding lines, where ice begins to float in the ocean and detach from the bed. Data was derived from fairly high-resolution aerial photographs taken from a distance of about 350 meters via NASA's Operation Icebridge, satellite radar interferometry from multiple space agencies, and the ongoing Landsat satellite imagery series, begun in the early 1970s. The team was able to discern that between 1979 and 1990, Antarctica shed an average of 40 gigatons of ice mass annually. A gigaton is 1 billion ton. From 2009 to 2017, about 252 gigatons per year were lost. The pace of melting rose dramatically over the 4-decade period. From 1979 to 2001, it was an average of 48 gigatons annually per decade. The rate jumped 280% to 134 gigatons for 2001 to 2017. Rignot said that one of the key findings of the project is the contribution East Antarctica has made to the total ice mass loss picture in recent decades. The Wilkes Land sector of East Antarctica has, overall, always been an important participant in the mass loss, even as far back as the 1980s, as our research has shown, he said. This region is probably more sensitive to climate change than has traditionally been assumed, and that's important to know, because it holds even more ice than West Antarctica and the Antarctic Peninsula together. He added that the sectors losing the most ice mass are adjacent to warm ocean water. As climate warming and ozone depletion send more ocean heat toward those sectors, they will continue to contribute to sea level rise from Antarctica in decades to come, said Rignot, who's also a senior project scientist at JPL.